All right, so we want to do Green's theorem. So let me read this mess and then we'll talk terms. So we want to let C be a positively oriented PW smooth, PW says piecewise, smooth, simple, closed curve in the plane. And let D be the region bounded by C. If P and Q have continuous partials on an open region containing D, then the line integral over C of P dx plus Q dy is the double integral over the region D of the partial of Q with respect to X minus the partial of P with respect to Y with respect to area. Okay, so first things first. PW means piecewise. Cool. Okay. Positively oriented means
above any of the axes.
So this isn't a plane.
Okay.
So I'm doing X, Y things here.
Above the plane.
Oh, no. Positively oriented. Everything's happening in the plane.
Okay.
And all this positively oriented thing is a way of walking around a curve. So what I want you to think here is
One direction.
yeah, counterclockwise. We're going to talk about exactly that in a second, but let's think counterclockwise. So if you look down the z-axis, you should be doing counterclockwise things. What's flipping this orientation going to give you? Like if I screw up and apply this to a negatively oriented curve, what's going to happen?
It's just be the same thing but negative.
Yeah, I'm going to get a minus sign, right? Okay, so this is just going to cause a sign error if I screw it up. So at the end here, we'll straighten out exactly what this means, but let's think counterclockwise. Cool? All right. In the XY plane, what's smooth mean? All right.
Continuous?
Yeah, differentiable, continuously differentiable. So that's continuously differentiable. What's simple mean again?
It never crosses.
Perfect, not crossing. Right, so not self-crossing. And what's closed mean?
It doesn't. Closed means that terminal plane and initial plane are the same.
Terminal plane and initial plane are the same. So that should read like you're going around a loop, right?
Yeah.
You guys see that? Maybe I could really replace all of this stuff with this stuff here means loop. Cool? So I'm going around a loop, I'm going the right direction. What the heck is D?
D is
So-
the region bounded by C, so it's the.
There's a loop.
Stuff, it's a shading inside.
Yeah, perfect. D's the stuff inside. So if this is C, D's this stuff. Cool. All right, what else have I got to break down here?
If P and Q have continuous partials on an open region containing D.
Okay, meaning that if I have problems, right, they're not happening on the edge of D, they're happening out a ways.
Okay.
You guys see that? They're not happening in D. You guys see that? So, just, hey, if P and Q have derivative problems, continuity problems with their derivative, that they're happening well away from the region you're talking about. Cool?
Yeah.
And then what's this stuff?
That just shows. That shows the curve.
So this thing's the line integral of some vector field f dr, right?
Yeah.
Where f is p comma q. You see that? So if I think about f as pq, then I'm just talking about the line integral over the curve of f.
Yeah.
And I'm saying somehow that's the integral around the region of the, what is this thing?
Looks like the curve.
said that was the curl just a couple of minutes ago.
Yeah.
So another phrasing, right? Another way to read Green's theorem in words is the circulation. Right, your book uses that for whenever you do a line integral around a closed curve. And really, I guess I should say this, shouldn't I?
Yeah.
Right, so another way to read would be to say the circulation of a vector field is the sum, right, the integral of
Some of the region.
about its curl.
Oh, that's correct.
Does that kind of make sense?
Yeah.
Like if I think about the curl as the kind of infinitesimal tendency to spin, there's a good reason that that's what this object denotes, but let's just assume that they meant something reasonable by the idea of curl, right? So I've got some little like, okay, here I've got a tendency to spin, and there I've got one, and here I've got one, and here I've got a little bit, right? If I want to know how much this thing pushes me around, then if I add up all the tendency to spin, I really should get that quantity. You guys see that?
Yeah.
That's really how you prove Green's theorem. You go break this thing into little triangular pieces, and then you show that curl has this reasonable interpretation. You just kind of do this thing. Cool? Positively oriented on this curve, which way is it?
Counterclockwise, so it's moving right, left to right.
Like this. You guys see that? One way to keep track of this is to think if you were a little fellow walking along this thing, right? If you were walking in that direction, which hand would be over the surface?
Which hand would be over the right hand?
Left hand.
Oh.
Right. That's all asked backwards. So when we say positively oriented, right, we of course mean left-handed.
Okay.
Cool. So you can just think the little guy that walks around the curve has to have his left hand over the surface. That'll help us when we're doing these in a couple of pieces. Cool? You guys want to practice a couple of these? The gist of this, the thing you need to remember is this picture, right? The curve C around the outside. Stay away from derivative problems. And the line integral is the sum of the curl. Cool?